And welcome back to Mechanical Systems Design. In this video, we'll talk about gears, and we'll focus on how they work and their efficiency and strength. As usual, this will work best if you've read the topic reading first, since we'll mostly synthesize that material, and we'll do a lot of exercises. So it'll be best to have pencil and paper and a partner to get the most out of this experience. So for some of you might hear gears as the topic and think that's a little niche. But actually, gears are really important. You could argue that they've played even an important role in the development of civilization because of their uses in agriculture and architecture and in the Industrial Revolution. The property that makes gears useful is that they can convert power from, say, low torque, high speed to high torque, low speed. And that's useful because very often your actuator or power source won't exactly match the task or application that you're interested in. And because of that, you'll find gears in many, many things around you that move, not just in clocks and cars, but increasingly in robots, like these dancing robots that may be coming to a drop-off site near you soon, who knows? So gears are fantastic. How can we learn enough about them to use them in our own designs? Well, let's start by talking about what they are. You might have kind of an image of them, but let's get more specific. In this video, we'll talk mostly about spur gears, which is a common basic type of gear, but the concepts apply to all kinds of gears. And the most important property is the pitch diameter. That is the diameter of this pitch circle that goes about midway through the teeth of the gear. If two gears have pitch circles that contact at a single tangent point, then those gears are properly meshed and they'll work as intended. And the ratio of the pitch diameters will be the gear ratio. That's a very important property of gear set. You can also see there's some number of teeth around the edge of the gear. And the ratio of the number of teeth to the pitch diameter is called the diametral pitch. It's the number of teeth per inch. And this is an important property because a smaller diametral pitch will result in fatter, stronger gears. The face width is just the width of those teeth. And then we have this pressure angle. If we zoom in on this shape of the teeth, you'll see that this is an involute shape. And if we draw a line that's normal to the tooth surface, and then a line that's normal to the center to center line, the angle between those two is called the pressure angle. That'll affect how the teeth are loaded and the efficiency of the gears especially. Okay, so that's what gears are. How do they work? I think a fun way to think about this is to imagine that you invented gears and then analyze them like a custom part. And really it just draws on exactly the same skills in statics and mechanics of materials that you use to understand your custom parts in the earlier projects in this class. So let's do that for gears. Here is our first exercise. So the question is the torque on gear 2 bigger, smaller, or equal to the torque on gear 1? Think about that. Come up with a way of arguing your point using statics, strength of materials, ideas. Work that out on your own for about a minute, then discuss it with your partner for a couple minutes, and then come back. And you should hit pause now. Well, we can see that the torque on gear 2 will be bigger than the torque on gear 1. And a simple way to explain that is that the interaction force between the two teeth is the same, but the leverage about the center of the gears is different. Gear 2 is bigger, it has a bigger radius, and so that same force produces more torque. And it turns out that the gear ratio will be the ratio of these radii. And this is my favorite way of remembering the gear ratios, thinking about this free body diagram and imagining the ideal case where there's no friction loss or anything. The torque on the second gear divided by the torque on the first gear is the ratio of the two gears radii. And similarly, you can take the ratio of the numbers of teeth, since that will be proportional to the radius. All right, Next exercise. So what is the total gear ratio from the red gear to the green gear, and why? So you can sketch, do free body diagrams, do a little bit of algebra, and try to come up with a convincing explanation of what the ratio is and why. You don't have to say, come up with a quantitative answer. Symbolic form is great. That's what we're going for. All right, so work on that yourself for a minute or so, then discuss your answers with your partner, and then come back, and you should hit pause now. All right, what we'll find out by doing our free body diagram analysis is that the total gear ratio from red to green will be the gear ratio from the first to the second gear times the gear ratio from the third to the fourth gear. So R2 over R1 times R4 over R3. And the way I like to think about this is that the torque on the second gear is the radius of the second gear divided by the radius of the first gear times the torque on the first. And that's exactly the same as in our first problem. And that same relationship will hold for the second set of meshing gears. Tau 4 is about equal to R4 over R3 times tau 3. And because the second and third gear are rigidly connected to each other, the torques are equal. So if we just take all these facts together and do a little bit of algebraic manipulation, we're going to see that the total gear ratio is R2 over R1 times R4 over R3. All right, now let's take a closer look at these teeth. And when they're moving, you can see that they're going to mesh and then unmesh. And if you look very closely, you'll notice that they're sliding during most of the mesh. If you pick a point on one of these gear teeth, you'll see that it's going to slide in and then slide out of contact with the other gear. They can't roll. That's not possible given the geometry. They have to slide some. And we'll see that the contact between the teeth moves on a line. And that's that line we were talking about earlier that is normal to the tooth surface. And that's because of this special shape of the teeth, this involute shape. And that actually is defined by trying to get the contact between the gear teeth to move along this line. That's how you derive the involute shape. So now that we're thinking a little more about how the gear teeth interact, a quick question. Between these two gears, which one is the driving gear and which is the driven gear? Is it the top that's driven or the bottom that's driven? Think about that individually for a minute or so, then discuss it with your partner for a couple minutes, and then come back. And you should hit pause now. Well, if we think about it, we can see that the bottom gear is going to be driven. And that is because the force has to be compressive. You can't have a sort of tensile contact force between the teeth. And the contact is on the face that's moving away from the driving gear. And you can also see this because there's a tiny gap on the other side. So the top gear in this case is driving the bottom gear. All right, next exercise. Why is there a friction loss? Try and explain this using your basic physics concepts. Take a moment to think about it individually, then discuss it with your partner, and then come back and we'll share. Well, here's one way to explain it. So the two teeth are in contact, so there is some normal force, and that means that friction is possible. So there could be a friction force there. And the teeth are sliding. So we know there will be a friction force. It's going to be mu Fn if we approximate it using Coulomb friction. And there's going to be displacement. And that means that work is done, work being force times displacement. And we'll also see that another way of understanding this is that that friction force has a lever arm about the center of the gear. And so the way that this energy loss is going to manifest is as a torque due to friction that counteracts the driving torque of the gear. Here you can see that normal force is causing a moment in this direction, and the friction force is causing a moment in the opposite direction in this configuration. Another reason that you could have given is that there's some friction at the supporting shaft. So if we have this tooth force, we need an equal and opposite shaft force onto the gear, or force from a bearing onto the shaft supporting the gear. And where we have a normal force, we can again get a friction force. And if the driving force of the tooth is tending to cause the gear to rotate clockwise, well, that friction torque is going to be trying to make the gear move counterclockwise. So we'll be fighting the driving torque, and that will cause a loss. So if we do some careful analysis of these free body diagrams and account for all the geometry, we'll find these relationships for the efficiency of that transmission that arises from those friction losses. So for the tooth meshing and unmeshing problem, we get something like the efficiency being equal to 1 minus the coefficient of friction times the quantity, the pressure angle, plus pi over the number of teeth on the second gear. And then the denominator will have something really similar, except there's a minus pi over the number of teeth in the first gear. And if we look at this equation for a minute, we can see that if the coefficient of friction is approximately 0, so you have perfect sliding, no losses there, then the numerator and the denominator are about equal, and we get an efficiency of 1, which is desirable. So low friction materials lead to good efficiency in the gear mesh. We can also see that if the numbers of teeth in the two gears get really high, then the numerator and denominator also become equal. And we again have perfect efficiency. So it tends to be the case that the more teeth you have in the gears that are meshing, the higher the efficiency. When we think about the way that the shaft sliding affects efficiency, again, if we have a really low coefficient of friction, we'll get nearly perfect efficiency. And we'll see that if the shaft radius is really small compared to the gear radius, then again, the second term is going to approach 0, and we'll get near perfect efficiency. So you want, again, a really big gear and small shaft if you're interested in maximizing efficiency. Now, just if you're a little rusty on efficiency and what that all means, remember that it is the power out of a system divided by the useful power into the system. And in the case of a gear set, that's going to be equal to, because the velocities are constrained, it'll be equal to the torque out divided by the gear ratio times the torque in. Now, notice that if you look at the efficiency of each stage, you'll see the power out of one stage is the power into the next stage. And the power out of that stage will be the power into the next stage. So it turns out that the total efficiency of the, say, a many-stage gear train will be equal to the efficiency of each stage multiplied by each other. And if the efficiency is all about the same, you'll get the total efficiency is about equal to the single stage efficiency raised to a power of the number of stages. Okay, so that's a lot to take in. Why don't you take a few minutes to consolidate these ideas, stare out the window, stir your coffee, and then come back and we'll talk about strength. I always think about this quote that Archimedes should have also specified something about the strength of that lever. I mean, it's a mean 3-point bending problem. Okay, here's a fun picture. This is an image of gears that are made out of a photoelastic material from ancient times, the 1960s. And the contours here correspond to regions of equal stress. So you can see that as we move across the line, say down here, probably the stress is pretty low. As we move up towards this contact point, stress is getting higher and higher and higher until we reach the contact. And similarly, if we start here and move towards this little internal corner here, the stress is getting higher and higher and higher. Here's another image that's probably a more familiar format to you, where we can again see this high stress right there, and then these high stresses in these little corners. Okay, so our next exercise, try to explain, why do you see this pattern of stress? And try to use some of the same strength of materials and statics concepts that we've used for the first part of this class. Take about a minute to work on this on your own, then discuss it with your partner for a couple minutes, and then come back. And you should hit pause now. Well, there are a few different things that we could focus on here. And one is this pattern of stress that should remind us of bending. So we have high stress up at the top here and at the bottom, and much lower stress in the middle. And that's kind of like a cantilevered beam problem. So if we draw the tooth like this, it starts to look a bit more like a cantilevered beam. And if we maybe approximate it even further, just that it fits our models exactly, we could have this, where we have this end load from the tooth force and a reaction force at the root, but we need this moment as well to keep this thing from spinning. And in this classic cantilevered beam case, we would find that the stress pattern, as hopefully is second nature now, is my over I, with the peak stress happening at the top and bottom of the beam. Well, we have a really similar equation for the peak stress in the tooth of a gear. And it looks like this. The stress is the tooth force times the diametral pitch divided by the face width times y, which is this Lewis form factor. It's an empirical value that captures things about the cross-sectional area moment of inertia of the tooth and the stress concentration effects. And if you manipulate these things, they look really similar. So there's another thing we could focus on, which is that big stress at the contact. And of course, when you have two very stiff objects that come into contact, the surface area over which the contact is pretty small, right? Because they have to deform in order to get a finite area instead of just a line contact. And so a very small area, pretty big force, we get a high stress. All right, so now let's apply some of this knowledge and try to answer the question, why are the teeth on the green gear bigger than the teeth on the red gear? So take a moment, come up with an explanation on your own, maybe spend a minute on that, then discuss it with your partner for a couple minutes, and then come back. And you should hit pause now. All right, one explanation is that the force is bigger on that second set of teeth. So if we think about just the middle two gears, we have that the torque is the same, right? Tau 2 equals tau 3 because they're tied together. So the torque of that second gear on the third gear is the same as the torque of the third gear on the second gear. But the radius of the second gear is bigger than the radius of the third gear. So you need a smaller force on the teeth of the second gear than on the third gear. And so that force at the interaction between gear 3 and 4 is going to be a lot higher than the one at the interaction between gear 1 and 2. And you know, the meshing teeth have to be the same size. So that fourth gear has much bigger teeth so that they don't break. So in the topic reading, we walked through a full derivation of the mass optimal gear design problem, and we came up with these relationships. The mass of an optimally designed gear should be something like 4 pi times the factor of safety times the torque it needs to take times the density of the material divided by the endurance strength of the material times the number of teeth to a power close to 1. And what we should see here is pretty logical, right? That more torque, higher factor of safety, that means more mass. This is something called the material factor. To have a lightweight gear, you'd like something that has a low ratio of density to endurance strength. And then this falls out too. The mass will scale with the number of teeth on the gear. So in a meshing set, what you'd like is for your smaller gear to have as few teeth as possible if you're trying to make something lightweight. And usually that number is around 8, below which things get really funky. And notice that's the opposite of the effect for efficiency, where we wanted a larger number of teeth in the gear. And this, of course, assumes that we've got an optimal face width, so that the width of the teeth is 16 times the torque times the factor of safety divided by the endurance strength of the material times the square of the diametral pitch divided by, again, the number of teeth to a power close to 1. Okay, so given these kind of messy equations, but that we kind of understand at this point, here's a question. Which gears would you rather have for a climbing robot? Would you rather it were made out of hardened steel or nylon? So take a moment and you can find properties that you need for these materials online pretty quickly and try to figure out which you'd prefer, hardened steel or nylon, considering both the mass of the robot and the inefficiency due to gear tooth sliding. Take a couple minutes to do this independently, then compare your answers with your partner, and then come back. And you should hit pause now. All right, well, what we can see is that steel turns out to be a better material for both outcomes, because even though it's denser, it's so much stronger that the ratio of density to endurance strength is smaller for hardened steel than for nylon. And similarly, the coefficient of friction for hardened, polished, lubricated steel is very, very low compared to that of, say, dry nylon. So if you're trying to design a system where you think you might have these trade-offs between, say, efficiency and mass, one thing to do is to try to aim for a common currency. So what is the effect of inefficiency? Well, it may be that you need to carry a heavier battery with you. And if you can make that conversion so that you're talking entirely about mass or entirely about energy, well, if your gear train weighs more, you'll have to put more energy into it. Then you can start to optimize because you just have one cost function. All right, so that's a lot about spur gears. There are a bunch of other ways we can incorporate gearing elements into our designs that are kind of fun to look at and think about. So here is an idler. So sometimes if you want the two gears that are supposed to interact to be offset by some distance so that their pitch circles don't intersect, then you can put an idler between them and transmit over a larger linear distance. Note that the total gear ratio here will be exactly the same as if these two gears meshed, but their rotation directions will be flipped. Here's an example of an internal gear. It's essentially the same as a spur gear, except the tooth shape is a little bit different, so they mesh properly. Here is a bevel gear. This comes in handy when you'd like the axes of the shafts that are interacting not to be parallel. And this is a 45-45 bevel gear set, but you can get them with lots of different angles to get various angles between the shafts. Here is a planetary gear, and this is the same kind of gear that you'll be using in your kits. And the way this works is that there's this fixed internal gear element here. Then we have this sun, which is just like a standard spur gear. And then we have these planet gears. And the thing that isn't pictured here is the thing that's being turned. So each one of these holes has a shaft through it, and that shaft is connected to a structure that's turning very slowly as those planets revolve around the sun. Here's another CAD image. We can see this a little more clearly. Just the sun kind of peeks out in the middle there, and then we have this triangular piece that's connected to this other spur gear that's enormous. And it's the rotation of this triangle piece that we're trying to achieve by spinning the sun. This is a worm gear. So a worm gear looks similar to a spur gear, except the teeth are shaped a bit differently. And instead of interacting with another gear-like shape, it interacts with this screw-like shape. And the screw here is going to be the driving element. These are generally not back drivable. And the cool thing about a worm gear is that you can achieve a really high gear ratio in a compact form. And in the topic reading, we tell you a little bit more about how to estimate the friction losses, which tend to be quite a bit higher for worm gears. Here's a chain drive. Chain drives work very similarly to spur gears, except it's the ratio of the sprocket diameters or tooth numbers that give you the gear ratio. And then by setting the chain length, you can place these at arbitrary distances from each other. You can also have an idler in a chain, of course, or a tensioner. And you can, a good example of this is in your bicycle where you need to change the diameter of one of the sprockets here occasionally, and that changes the length to get everything to fit properly. So a spring-mounted idler allows that to happen. A similar idea is to use a wire or rope drive, where you have a capstan or drum or pulley that a rope wraps around. Now, this particular drive would be very, very weak because the rope only wraps around about half a wrap. And sliding is a huge problem in these kinds of systems. So if you design a capstan drive or a winch with a drum, you want to make sure that the rope or string wraps a few times around before terminating on the capstan or before it unwraps and goes to the next element. Otherwise, the rope will slide. It's very hard to tension that enough to prevent sliding. If we want to get really crazy, we can start adding linkages to our systems and funny shaped gears. And you actually see stuff not quite like this, but with unusual gear shapes out in real machines for various purposes. And if we add mechanisms, then things can get super funky with components sometimes stopping and starting, moving only in one direction while everything else is reciprocating, stuff like that. This is one of my favorite examples of gears. This is a scanning electron microscope image of the joint of a grasshopper. And this grasshopper has evolved gears in its leg joint so that the two legs involved in a jump move exactly synchronously because it goes so fast, and a little bit of different timing would result in undesired flight patterns. So gears, evolution is amazing, and it's even discovered gears. Okay, so at this point, you know a whole lot about what gears are, how to estimate their efficiency, and how to estimate their strength. A good thing to think about after this video ends is how would you characterize a gear set that you were given? How could you use these models we've talked about to design tests that would reveal the characteristics you care about in that gearbox? And first, try to figure out what are the characteristics, then what equations contain them. The simplest possible equation that contains them is probably the best. And what would you need to measure to provide inputs to that equation? And what conditions for your test would make this characterization simplest? And we'll be talking about this problem together in our coaching sessions.